start this. Okay. So we're doing things a little bit weird, but we did lab 1 last week. Lab 1 isn't due until the 20th, right? So I want to give you guys a lot of time for lab 1. So the first one, trying to get the kinks out, just kind of try to get organized. But in general, they're just going to be due the week after, right? So we have labs on Fridays. It'll be due the following Friday at midnight. And so lab 1 is due. I'm always hesitant to say like Monday, January 20th, because I always screw one of them up. It makes it very difficult to decipher, but I'm pretty confident Monday, the 20th is a day. Yeah, cool. 20th. And for all my online assignments, which is going to be a lot of this class, they're just due at essentially midnight, right? 11:59 p.m. Okay. If we go to Moodle, where am I here? Yeah. I've got the due dates in the week 1 bin here. So assignment 1 is due this Friday at midnight, okay? And you'll see down here, I just posted assignment 1, and just give it a go. It should just take you right into, it's called My Open Math. It's a free kind of online, so that's why you don't have to pay anything for it. It's my first time using it though, so that's why I'm a little bit, yeah, see how it works. Because when I click it, it doesn't act like a student for me, so I can just go preview assessment, and then that's what it'll look like. But it should just take you straight to that assignment. So if you give that a go and that's not what it looks like, then just please just let me know and I can figure it out. Yeah. So where's that? Yeah, so this is just like in-class assignment. So the one with the M on it is just the in-class assignments, right? And then there's a lab assignment. So there'll be separate marks, right? Because you've got so those little normal M assignments, let's call them my open math assignments, those are counting for 10% of your grade, and then the lab assignments are a separate 10% of your grade, right? So they're 2 different grades. Okay. All right, so January 17th, gave it till Friday. We finished chapter 1 last day. So you do have everything that you need. There's 2 things that I want to talk about today, but besides that, you have everything that you need. And so assignment 1 is due this Friday, January 17th, also at 11:59. Assignment number 1 notes that I just want to talk you through, because though these things are sort of mentioned in chapter 1, they're not really. So what we did a little revamp and rejig with the old chapters, and so these questions match the old chapters, which means nothing to you, and that's okay. But So the assignment questions talk about explanatory variables and response variables, and I have those mapped out to talk about later, but I'll just tell you what they are. They're not that weird. So on question 5, you need to know the difference between an explanatory versus a response variable. Okay. And so I'll start with a response variable because that's usually the one that we're interested in. In fact, in a research question, right? So we talked about tomato plants, I think, last day, right? So we're growing our tomato plants, right? And so our research question would be about maybe the height of our tomato plant or how many tomatoes it yields or something like that. So the core thing that we're interested in measuring is our response variable. Everything else that we measure, things like how much sun it gets, how much water it gets, all those are explanatory variables. Okay? And so the response variable in a research question the variable of interest is the response variable. How many tomatoes do I get off of one plant? Let's make that our response variable. Whereas the explanatory variable, explanatory variable is any variable that you've collected that might help explain changes in the response variable. Okay? So any variable collected that might help explain changes in the response variable. So there's going to be one response variable. Everything else that you've collected is an explanatory variable. Any questions about those? So then in question 9, it talks about a statistic versus a parameter, which we were actually gonna, or we still are, gonna talk about today. But I just want you to know that even though it's stuff we've covered in chapter 2, we can use it in chapter 1. So I just want to highlight that here. So a statistic is anything that we've measured that's coming from a sample, right? And so just S and S, right? Statistic, a sample. And a parameter is anything that we've measured that comes from a population, P and P. So a statistic is any value calculated from a sample. Right, S and S. So a statistic is anything from a sample. So if you've collected a sample and you calculate the mean, or later today we'll talk about the standard deviation, right? All those things that we can calculate from a sample, all those things would be considered statistics, right? Whereas anything that you've calculated from a population or anything that you're kind of saying about comes from a population would be a parameter, right? And so even though we can talk about the sample mean and the sample standard deviation, the population is also going to have a mean and a standard deviation. Now, we haven't talked about those yet, but we will. So a parameter, oops, fun, but not what I wanted. A parameter is any value calculated from a population. Any value calculated from a population. And just remember P and P. Any questions about those? So those are just little heads up for assignment 1. But besides that, you have everything that you need and more to answer those questions. So in the lab, we basically covered all there is to do about categorical data for now. So section 2.1 will be really brief. And don't worry, it was going to be brief either way. Categorical data. Categorical data is kind of boring in the sense that, well, there's not much we can do about it. In terms of summarizing it, we usually look at the counts in each category. And in terms of visualizing it, we make a bar graph, or we can make a pie chart, but we should make bar graphs, right? We can look at more than one variable, right? We can look at 2 categorical variables, looking at segmented bar charts like we did in the lab, right? And so, but beyond that, there's not much else we can do with categorical data for now, right? Later on, we'll come back to it when we talk about proportions, but for now, that's basically all we can do. So categorical data. Categorical data, or qualitative data, depending on what you like. I'll use categorical, but it's more to get you kind of into the groove that if you see qualitative, right, think quality, category, right? And so qualitative data is often summarized in a table, right? Which we did already in the lab. Often summarized in a table. Think of pivot tables from the lab. If we're only looking at one variable, right, what we're making is called a frequency table. Right? And so if we are considering only one variable, the table would be called a frequency table. And I'll just go in and steal an example. No, I don't want that.
man. So here, something that looks like this, right, would be a frequency table. It's talking about the spam data, and the spam data appears, and maybe I should have stolen it. Anyways, I guess I can go back there. Come on. You guys probably are familiar with the spam data because it's from chapter 1. There. So the email 50 data, or I just call it the spam data because it's talking about the spam. And it's kind of typical. So this is how you kind of perfect an algorithm essentially. So you have some emails or whatever that you've classified as spam, right? And so they're either yes or no spam. And then they look at things like, well, what number of characters do you have in that email? How many line breaks are there? What's the format of it? And are there any numbers? And if so, are they small, big, or none? I think it's just no number, a small number, or a large number. So this here, this is our data matrix, or just our spreadsheet essentially, right? But then here is our data summary. And so here is where you can find out, well, what are all these things, right? What are they measuring? What are the possible outcomes? And usually that's how we can determine if it's a categorical variable or a numerical variable, right? And so spam is either yes or no. And if that's what we're interested in figuring something out about, right? Are we trying to be able to capture spam better, right? Then the spam variable would be our response variable, right? All the other variables would be just explanatory variables, right? The number of characters, the number of line breaks, the format, and how large the numbers are, right? Those are all helping to try to identify whether it's a spam email or not, right? And so if we're just looking at the number variable and we just want to summarize it, because it's a categorical variable, right? None, small, big, 3 categories, then we can make this frequency table. But what we did more in the lab was, well, what if we're concerned with more than one variable, right? Then we want to make a two-way table or a contingency table. That's the same thing. You'll find this whole course is me saying, oh, there's 2 names for everything, at least 2 names for everything that we'll talk about. So it gets a little confusing, but that's part of my job, is just to walk you through and tell you what they all could be named so that you recognize them later. So then we could look at a two-way table or a contingency table like this one. Actually, let's get this down here. Two-way table or contingency table. All right. I'll keep going. Helps it doesn't just help, it summarizes the relationship between two categorical variables. Usually what we'll find is that, well, for just the way our minds work, if I tell you is 400 out of 3,554, is that hugely different from 495, right, versus 2,659? So we have a hard time dealing with just raw counts, especially when it's not out of a nice number like 100 or 1,000 or 10 or something like that, right? So those numbers we're able to deal with kind of easily. But when it's out of a total, let's say the grand total, 3,921, well, that's hard for us to kind of think about and compare values, right? So usually what we do is we take proportions, right? So we divide one of these numbers by a total. And what gets confusing is we have column totals. So these down here, we have column totals, we have row totals, and then we have the grand total, which I should have scooted down a little bit, but the grand total is here. So let's do green. So here, this is a grand total. These values here are the column totals. And then these values here are the row totals. So depending on if you want a row proportion or a column proportion or a grand proportion, right? So we can develop proportions based off of these totals. And so proportions are often more informative than raw counts. And in a contingency table, we can find the row or the column or the total proportions. So in a contingency table, we can find, oops. We can find row or column or total proportions. For example, I'll just steal this again. Copy. Oh, maybe. Clean it up a bit. Yeah. If I use the row totals, I'll break down a bit, reach it. Right. Let's talk about each individual cell in here.
right? So there's 149 emails that were classified as spam that had no numbers in it, right? So there were no numbers appearing. There were 168 spam emails, right, that had a small number in them. I think less than 1 million or something. We had those. And then there were only 50 emails that had big numbers in them that were classified as spam. So if we just think about that for a little second here, right, then it looks like if it has big numbers, right, it's less likely to be a spam email, right? Just looking at these numbers, or at least that's what it looks like to me. How we can figure that out is, well, the total number of spam emails was 367, right? And so 149 out of 367, right, were spam emails with no numbers. 168 out of 367, right? So now when we're taking these proportions, right, and usually the most common proportions or kind of proportion lookalikes that we deal with are percentages, right? And usually we like percentages, right? We understand percentages, we get it, right? And so proportions are just percentages. Yeah. So here, a proportion is basically a percentage. I say basically because a percentage, you have to multiply the proportion by 100%. So for example, the proportion of spam emails with no numbers would be 149 out of 367. And I managed to forget my calculator. I'll just use my math. It's not that important. 149 out of 367. I'll use equals, but 0.405 99455. Probably what happens in your head is you would just convert this automatically to 40.6% and then move on, right? But you have to, so for this course, we have to keep track of, okay, well, this is a proportion, right? So a proportion is between 0 and 1. And then a percentage is just a proportion times 100%. Right? And so a proportion is a number between 0 and 1. Whereas a percentage is a proportion times 100%. So usually we want to deal in proportions, right? And so now, or take it one step further and change them to percentages, right? But as long as you've kind of kept track of, okay, well, this is a proportion, this is a percentage, right? Then you're safe. So I say proportions, but you can just as well convert them to percentages as long as you keep them straight. Yeah. And so what that's saying is that 40.6%, right, or 0.406 of the spam emails had no
no numbers in them, right? So this here, this is a row total, right? The total number of spam emails, which makes our proportion a row proportion. So that's something you'll want to keep in mind, right? So whatever value you divide by, right, that's the group that you're talking about overall. And so out of the spam emails, right, that's where the 367 comes from. If we want to talk about out of the emails that had no number, right, then our total is 549. Then 149 of those were spam, right? So it just depends on what we want to talk about. Yeah. So or I guess we should talk about all the emails, right? Out of all the emails analyzed, the 3,921, right? Then we can talk about 367 of them were spam, right? Spam overall, doesn't matter what number type they had in there. Or you can drill it down even further and say, well, 149 of those were spam with no numbers, right? So it just depends on what level you want to talk at. To visualize categorical variables, we should use bar charts. Bar charts. Just kind of interchangeably, if I say a chart, it can also be a graph, right? So a bar graph. Pie charts are popular, but they shouldn't be, because the whole point of visualizing data is to get a clear, concise view just at a glance, right? And so what happens with pie charts, unless you're only looking at two categories, male, female, it's very hard to see how big those slices are, right? And so, to take it even further, if you've only got two categories, male, female, then you could just say, well, there were 30% females, and then you know the rest is males, right? And so you just need one number to communicate that. You don't actually need a graph. And so, so there's things like that, kind of hang-ups in the data viz community. We do not like pie charts. Okay, so pie charts make it really hard to see the size of very similar groups. Okay, so pie charts. Pie charts make it difficult to see differences between groups if they are very many or similar. Right. So for example, I'm going to draw, well, not very good, was it? I'll even cheat there. So now, right, let's say here's one group. Here's another group. Right? All of these slices just represent each of the units in the category, right? Here's another group. Here's all the other groups. If you had to pick which one's the smallest, for example, that's going to be very difficult. It's easy to pick the biggest one, but that's about it, right? Even those two medium-sized ones, I just kind of free-handed it, right? So one looks a little bit smaller, but it's very hard to look at these and to be able to really say something distinct about them, right? So you could say something like there's one big slice, two medium slices, and I don't know, 5 small slices, but that's not very helpful, right? Versus a bar graph where you've got a bar for each category. So here's our big bar, here's our medium bar, and of course it's not fair because I'm drawing these things, right? But even a small difference between those two medium bars, it's just easier for us to see, right? And so what you want to keep in mind is if you're making graphs, the whole idea is you should be able to just throw a glance at it, understand what's going on, and then turn away, right? And so you don't want to be spending a lot of time kind of diving in and saying, well, this one looks a little bit bigger, right? And so, and then you could have the rest of them maybe like that, right? And so we're able to see these kind of smaller differences. Okay. So that's why we make bar graphs in the lab, right? Because that's what we should be using. There's even fancier things like the segmented bar graphs, where each bar is broken up into more categories, right? So we can incorporate 2 categories into our bar graph. But in general, bar graphs are the way to go, right? And definitely not something that you should be making by hand. It is something that you should be making in Excel, right? And so I've got my favorite. Got a little grainy, I guess. How can I make it fit on one screen? So he's made a pie chart of his favorite bars and a bar chart of his favorite pies. So I'd say pie charts are good for, well, jokes mainly. So anyways, it's too grainy. I can't see how he's measured his favorite bars. If he's gone around and collected a sample and asked people, what's your favorite bar? What's your favorite pie? But I guess maybe that's not the joke. So shouldn't look into it too hard. But anyways, so any questions? So that's all we're gonna kind of touch on for categorical data for now. We will get back into it because just as a kind of an overview of the course, we start by analyzing means, which is just an average, right, for numerical data, and then we kind of apply the same methodology to analyzing proportions, which is what we were talking about here, right? So we will have seen proportions before here, but we'll learn to analyze them later. Okay. All right. No questions? No. So let's get into 2.2, which is on numerical data. So numerical data is just in general, or at least to me, far more interesting than categorical data. because there are things that we can do, right? We can calculate the average, for example, and already just knowing the average, we know more about this data than we do for just counts for categorical variables. And so numerical data is a little bit more of a sophisticated beast. And so we'll need more than just counts in order to summarize it. In fact, we need to look at three things. Right? We need to look at the shape of the distribution, we need to look at the center, and we need to look at the spread. Okay. So to summarize, numerical, right, or quantitative if you prefer, or quantitative variable we need to consider three things. The first one is the shape, okay, the shape of the distribution, which means we have to visualize this thing somehow. Just like we did with a bar graph. A bar graph is just a visualization of a table, right? And so if we've got numerical data, then first thing we do is we visualize it, we look at the shape of it, and then from there, from the shape, we'll be able to determine, well, what is our best measure of center and spread? And so the first thing we're going to look at is the shape. So often, a histogram, which I'll show you in a bit, a histogram is the easiest way to visualize the shape. Way to visualize the shape of a distribution. The second thing we need to talk about is going to be the center. So where is this thing centered? So the center, depending on the shape, right? That's going to determine what our best measure of center is. And so first we look at the shape, and we'll obviously talk more about it. Then we look at the center, and then based off of the center, it'll have a matching spread that we talk about. Okay? And so today we'll just go through and talk about all of these so that we know what all the shapes are, what all the centers are, and what all the spreads could be. Okay? So for the center, depending on the shape, we will be able to determine the most appropriate measure of center. And then finally, the spread also depends on the shape and the center. Right? You could just say it depends on the center that you've chosen, because the center depends on the shape, right? But I just want to highlight that it all hinges on what the shape of the distribution is. So the spread also depending on also depending on the shape. And I'll put in brackets and center, right? Because shape determines the center. We will be able to determine the most appropriate measure of spread. So these are the three things that we need to keep in mind, because we need all three of these in order to completely summarize a numerical variable. So first, let's talk about the shape, and then we'll talk about the centers, and then we'll talk about the spreads. We'll tie it all together. So for the shape, there's lots of different methods that were developed to try to look at the shape of a distribution. Like I said, the most common now is the histogram, because even our phones can make histograms, right? But there are a lot of methods that are still around, mostly because, well, I say we can get rid of them. I don't really care about things like a stem and leaf plot or a dot plot or anything like that. To me, they're just poor man's histograms. We'll just talk about them a little bit. But these things were all developed in a time when it was very expensive to make a histogram, right? And so we had to find other ways to do it. So many methods have been developed to visualize the distribution, of a numerical variable Some of these are introduced in the textbook. Some of these are introduced there are things like a dot plot, which is where it starts. A dot plot. There's also a thing called a stacked dot plot. Which I'll just show you. So here's a dot plot, right, from the textbook. So it just shows a dot for each data point. And so if we see a lot of dots, then we know we have a lot of data points there. And if there are not very many dots, then we know there aren't very many data points there. And so that's going to help us think about the distribution. Same thing with a stacked dot plot, same idea. If instead of overlapping the dots so that they become darker, you can just stack them on top of each other, which to me is basically a histogram when we get to it. But anyways, for now, those are options, but not something that I want you to do or anything like that. Of course, our main player is the histogram. A histogram. Here's a histogram that I'll steal. So what a histogram does is
it takes, so we've got the number of characters, right, in thousands from our email data, right? And so each email had some number of characters in it, right? Just counted in thousands. And so then the histogram just makes bins. So it essentially makes categories, but it's on this continuous scale, right? And so between 0 and 5,000 characters, right, there were around 20 emails like that. Right? And then between 5 and 10,000 characters, there were roughly, I don't know, 13 emails like that. And so it makes temporary categories for each of your numbers, and then they get put into these bins, they're called, and then they grow as you increase the number of items in there, right? And then we're able to see, well, most emails, right, or the largest kind of bar here, the largest group, I should say, is between 0 and 5,000 characters. And you can usually figure out what the bins are because it will have little cutoffs, right? Starting at 0, there's a tick, and then 10. So I'm just assuming it's at 5. So this is a histogram. Right. And I'll just do a little. Each value is placed in a bin and the frequency in each bin is shown. We can also do a stem and leaf plot. I'll move this over here. So a stem and leaf plot I call it a poor man's histogram, right? If you don't have the tools to make a histogram, so a poor man's histogram. And the textbook goes through and explains how it's done, but you take each of your data points, right? And so, and then you figure out what your stem is going to be, right? And then you've got a leaf for each data point. And what ends up happening is you get something that looks like, so here it goes through an example, it gives you a data set, and then you can sort them out, and you've got stems and you've got leaves. And then here, yeah, which one, it doesn't matter. These are both stem and leaf plots. The only difference is that here, these ones are unsorted 9852, here 2589, doesn't matter. I don't really care about stem and leaf plots. If you have to do one, I'll warn you, but until then, don't worry about it. And just be able to recognize it. Right? And so what you'll notice though is regardless of if these guys are sorted or unsorted or sorted in here, right? If you just take this and you kind of lean your head this way, does this look like a bar? This look like a bar? This look like a bar? Right? And so now you're back to this histogram, right? And so the idea being that, okay, well, we can visualize a distribution by essentially making these bins, right? and making these bars. And it's okay to have gaps in your stem and leaf plot. In fact, if there are gaps, you should show them. But yeah, so this to me looks like a histogram, but it's just handmade, right? An important thing if you're making a stem and leaf plot, right, then it's going to be important that each of these numbers in the first row, right, or in the first column, take up the same amount of space, and then these guys take up the same amount of space, because you don't want to have, you know, your biggest row all squished together, because the whole idea is to show how many are in each bin, right, or on each stem. So that's a stem and leaf plot. And then finally, we can look at a box plot. Of all the things that I might make you draw by hand, this is one of them. Okay. And so a box plot, well, we'll look into more detail, but it's just going to summarize. It's going to be a graphical representation of the 5-number summary, which we haven't talked about. But I'll put it here to plant the seed. It's a graphical summary of the 5-number summary. So many summaries. Okay. So let's talk about the shape then. So here are the things that we can use to look at the shape, right? So what is this thing going to look like? And so for us in this course, what we're mainly looking out for is a normal distribution or a bell curve distribution. Okay. And so when looking at the shape of a distribution, we are looking for a bell-shaped curve called the normal distribution. And I'm even going to capitalize the normal to emphasize that it's a name of a distribution. So it gets confusing, right? Because, oh, that's normal, but normal actually means a distinct shape. Just like a circle is a distinct shape, a square is a distinct shape, right? A normal distribution is also a distinct shape. Also called the normal distribution. And let's see if I can, first normal distribution of the term here. Hey, it turned out pretty good. Usually mine's like lifted off on one end or something like that. Right? And so this distribution, right, is symmetric, and it's got a peak, one peak, and then it's quickly closing off on the sides, right? So this is a normal distribution, and this is the one that we're looking for. Yeah. Show me how it's done. Oh, so if you have, sure, let's talk about, so if you have something like this. Yeah, that would be called something else. And I think at the end of the day, the data would look something like this, right? Because what we have is we actually have data underneath. So underneath these curves, so this is just the axes, and so this is just axis. but underneath these curves, we have data. Right, and so I'm trying to visualize what just the U would look like. I'm sure there's a name for it, but I just don't know it. Yeah. I'll delete this for now, but we will talk about that one again, just briefly. So for us, what we're always looking for is a normal distribution. And the reason for that is there's so much that we can do if we have a normal distribution. So a lot of what we're going to do is we're going to just check assumptions later on, just so we can assume that we have a normal distribution. But at the end of the day, this is what we're looking for. Okay. We know that our data, especially if we have a smaller data set, right, our data isn't going to look beautiful and smooth like this, right? And so what I want you to kind of do is, well, let's look at something like this. Could I be convinced that this is going to look like a normal distribution? No, right? Because I've got this abrupt cutoff here, and that's my highest peak. And so how I want you to think about it is just imagine just kind of throwing a blanket on here and just look at the grand scheme of things, right? And so here, if I threw a blanket on here, this would look more like this, right? And that's okay, but that just means that we have a skewed distribution. Let's see if I meant to talk about, yeah, that's okay. So if we have, dealing with a page break here, if we have something that looks like this, this is a skewed distribution, and it's always skewed in the direction of the tail, which means that this is a skewed right or positive skew, if you want. Distribution. Okay. I'll put a note here. The skew is always in the direction of the tail, right? In the direction of the tail. Which to me used to always feel backwards, because I always wanted to talk about the lump, right? Where's the lump? Well, it's skewed in the direction of the lump. But for us in stats, and this is kind of a good warm-up, in stats, we always want to talk about these extreme observations, right? What's the probability of seeing something that extreme, right? And so we're always concerned with these extreme values, which would be the ones out in the tail, right? And so for us, the skew is always in the direction of the tail, because those are the values that we're interested in. We're not interested in the ones that behave like everyone else. We're interested in these kind of extreme values. Okay. And so same idea here. Could have something that looks like this. Right. Well, this is skewed to the left, or skewed left, or negative skewed. Skewed to the left. Could also call it a negative skew. It's always skewed in the direction of the tail. The only other one that we might mention, although we already saw it, is something like this. This would be called a bimodal distribution. Because these two humps, this is a mode and this is a mode.
in fact, all of these distributions, the highest peak is a mode. So all of these have modes, and so for the number of modes that you have, well, you're going to count how many distinct peaks you have, right? And so I don't want to talk about, I don't want to hear you talk about this being a mode, for example, right? Because we want to have distinct peaks, right? So here, this is a mode, right? And then it drops down, and in general, it smooths off, right? And so we don't want to get picky and kind of get hung up on things like this. It would have to be a clear, in your blanket, right? If you draped a blanket over this, it would have to be a very distinct other mode, right? And so what I always want you to remember is that we've got some data size here, right, or some sample size here. I don't remember what it was. 50, probably. It's called email 50, I'm assuming. Right, so here we've got a sample size of 50. That's not very large, right? If we collected more data, what's very likely going to happen is that these things would kind of fill in and everything would just kind of even out, right? And so don't be too picky on finding modes, right? They're going to have to be very distinct, very clear modes. But so here, the normal distribution, we can summarize it as a symmetric unimodal, right? So one mode distribution. So I've got space here, but the normal distribution can be summarized as a symmetric unimodal distribution. So those are all the shapes that we're going to care about. There's lots of other ones. If you keep going in stats, then there's lots of other distributions. But for now, these are the only ones that we're concerned with. Right? And the main one being the normal distribution. So if we have a normal distribution, we said that we're so powerful with all the things that we can do, right? And a lot of that hinges on, well, if we have a normal distribution, then the mean or the average is our best measure of center, right? Which opens up a whole set of tools for us. And so if we have a normal distribution, the best measure of center is the mean. More commonly known as the average. More commonly known as the average. In this course, right, I usually, depending on what sounds better, usually there's nothing else that determines which term I use. I'll use the mean, the average. Now in the beginning, I try to use both, right, just to kind of emphasize that they're the same, right, until we've got that link between because we all know the average, right? If I ask you to find the average of the numbers 3, 2, 1, and 4, what would you do? You would add them all up and divide them by 4, right? However many you have, your sample size, right? So I just gave you a mini sample, right? You add them all up, you divide by your sample size, and that's your average, right? So we all know how to calculate the average, but we probably don't know what that formula would look like, right? And so first we'll say that the sample mean is denoted by a lowercase x with a bar over it, right? And we can just read it as x bar. While the population mean is denoted by mu. Okay, so this is a Greek letter mu, and just to kind of show you, it starts off low down here and then it kind of goes. Mine look nicer when they're small. Right, but so this is a mu, oops, which you can just spell mu. Which means what? It means that x bar is a statistic. Remember from beginning of class, we said a statistic is anything that we've calculated from a sample, right? And so our sample mean is x bar, right? Whereas mu is a parameter because it's something that we've calculated or pretended to calculate from the population. So mu is a parameter. And in general, almost all parameters, we could say all, if we're not being too picky, are denoted by Greek letters, right? And so to keep these things straight, because what gets so confusing for a lot of people is, well, I know the average, but we don't just know the average, we either know the population average or we know the sample average, right? We know the sample mean or the population mean. There's going to be two means because remember the whole goal of statistics was to take a sample from a population, do math on it, right? Do stats on it, do calculations. But then the whole goal was to be able to say, well, based off of this sample mean, for example, I know something about the population mean. Then I think the population mean is going to look like this, right? And so statistics is just taking statistics, right, in terms of something that we've collected from a sample to learn about the parameter, right? And so we're always going to have this relationship between, well, I've got a sample thing and a population thing, right? And we have to keep track of them. And so the easiest thing to remember is that, okay, well, all the population things will be denoted by Greek letters. Yeah. I'll say all. All parameters will be denoted using Greek letters, right? So your Greek alphabet is going to get pretty good. Now we've got some go-tos, right? Mu, alpha, beta. Anyways, so so just in general, all parameters, we're going to use Greek letters. Right? So we said, okay, well, X bar, I'm sorry, I have to use all my time. And I've got 2 more minutes. X bar, we said, well, if we had to do it just, if I am given a set of numbers and I have to find the average, then I would add them all up. So what that looks like here, and I'm just going to do very, very basic summation notation, but this is a Greek capital sigma, and it just looks like this E. And this is summation notation. Fun to say, fun to do. So summation notation just says, okay, well, sum up all the things that follow this capital sigma. In our case, all the x's, where the x's are all our observations. Sum up all your observations. Oh. And then divide by n. Remember that n, we introduced kind of sneakily last day, n is your sample size. So for next day, I want you to just kind of go through 2.2 again, just kind of breeze through it because we've talked about it now, but also try to read 3.1 to 3.3. And I think you're gonna like what you see. Anyways, see you guys on Wednesday. Hey guys.